Hello everyone, my name is Stu Adler. Welcome back to Introductory Lectures in Thermodynamics. Over the last two episodes, we've been exploring how systems of molecules transform upon changes of energy content, and how workers measure and describe this in terms of the internal energy. However, as we discussed several weeks ago, there are really two issues that we need to address in order to fully understand the aggregate behavior of molecular systems. Besides energy, the other important issue is probability, which influences the average way in which molecules are likely to be arranged in a system. This brings us to today's topic: entropy and the second law of thermodynamics. Entropy is a state property that helps us predict how a group of molecules will behave probabilistically. When combined with internal energy and the first and second laws of thermodynamics, we have the principal tools needed to predict the spontaneous behavior of a group of molecules. I'd like to begin our discussion of entropy with this now famous New Yorker cartoon by Mark Thompson. It depicts a young boy in his room, surrounded by a mess of clothes, books, and toys. His mom is standing in the doorway with a load of laundry and an annoyed expression on her face. The boy, realizing he's in big trouble, announces that it's not his fault his room is a mess. It's just entropy. This cartoon draws on a widespread view of entropy as a measure of disorder. The boy recognizes that he's in trouble for this disorder, but rather than accept responsibility, he deflects blame by invoking the colloquial view of the second law, which is that the universe naturally tends toward disorder, so it's not his fault. But this raises the question of what it really means to be disordered. For example, as a graduate student, I once went to visit Leo Brewer, a leading pioneer of high-temperature chemistry, in his office. His office was not a traditional office. It was an old abandoned laboratory in the sub-basement of the Berkeley College of Chemistry. It was an absolute mess, papers and bits of equipment strewn everywhere, covering every possible square inch of work surface. In the middle of the room was a large lab bench stacked 3 feet high with about 50 sagging stacks of paper and journal reprints. After warmly receiving my visit and answering my naive questions about oxides dissolved in salt, he recommended that I read a particular paper from the early 1960s on the subject. He then walked over to one of the sagging stacks of papers on the bench and grabbed the protruding edge of a paper buried about 2 feet deep in the pile, pulled it out, and handed it to me. Suddenly, I realized his office was not a mess at all. It was a carefully organized library of the most important work in his field, organized laterally by subject and chronologically by depth, with a highly detailed index kept safely in his own mind. Returning to this cartoon, we see here a particular arrangement of clothes, toys, and books that appears to be a mess. But how do we know this arrangement isn't a carefully orchestrated alternative to putting the toys away in the closet? For example, when I'm working in my woodshop at home, it starts to look a lot like this, but I know where all the tools are because I remember where I last used them. So the description of a room as messy is really a subjective value judgment, not a meaningful quantitative description of its general state as a functional workspace. Over the next 20 minutes or so, I hope to convince you that this colloquial idea of entropy as a measure of disorder is actually the wrong way to think about entropy. This vague association with disorder obscures the true meaning of entropy as a quantitative property and undermines understanding of the second law. By the end, I hope to show you that the second law is not a mysterious force that drives systems to disorder. It's an obvious natural consequence of molecular motion and probability. To more clearly frame why probability matters, consider our simulation of two-dimensional Lennard-Jones fluid. Our results illustrated how energetic interactions among molecules leads to complex spatial distributions, including phase separation. However, when we went to model this behavior using a mean field approach, using the van der Waals equation, we found we could only explain the behavior at higher temperatures, where the system is a gas or supercritical fluid. Upon decreasing the temperature, this model breaks down, predicting negative pressures and failing to predict the formation of two phases. So what is it that a molecular dynamics simulation captures that a mean field theory, like the van der Waals equation, does not? Both approaches consider attractive interactions between molecules. However, the way they do so is quite different. The mean field theory presumes a homogeneous average distribution of the molecules everywhere, and predicts average properties like temperature and pressure using a continuum approach. In contrast, the MD simulation does not prescribe this distribution. It merely enforces Newton's laws of motion for each molecule under the influence of attractive interactions. During the simulation, the values of kinetic energy and the force on the walls of the container fluctuate as the molecules move around. We then calculate the time average of these fluctuations and call this temperature and pressure. This means the simulation is not just considering the energetic interactions. It's also calculating the natural fluctuations in structure and properties, and thus, indirectly, their relative probability. As we've seen, these structures are not perfectly random or uniform. Even a supercritical fluid, when examined on a molecular level, appears clumpy. These naturally forming structures have a major impact on potential energy and other properties, including condensation as a separate liquid or solid phase. Given the importance of these fluctuations, one question to ask is whether we can rely on time average statistics, as provided by the simulation, as a general approach to calculating probabilistic tendencies of molecules. Unfortunately, even with the fastest computers available today, molecular dynamics calculations are still limited to fairly small numbers of simple molecules over relatively small time periods, a few nanoseconds. Yet the field of thermodynamics is more than 150 years old, much older than the invention of computers. So what have workers been doing all this time to understand the probabilistic tendencies of molecules? One important approach has been a theoretical framework known as statistical mechanics. As defined by one of its chief practitioners, David Chandler, statistical mechanics is the theory with which we analyze the behavior of natural or spontaneous molecular scale fluctuations. The magnitude and timescale of molecular fluctuations dictates many properties of a homogeneous phase, as well as the stability or instability of phases and other structures formed by molecules. However, unlike an explicit MD simulation, statistical mechanics seeks to model these fluctuations in terms of statistical probability, rather than the detailed time trajectory of the system. Although a full treatment of statistical mechanics is beyond the scope of this course, I think it's worth covering some of the basics, as it provides a very useful starting point for defining entropy and understanding the origins of the second law of thermodynamics. A common starting point for examining the role and axioms of statistical mechanics is to consider an isolated system of volume V containing n molecules with total energy U. Recall that according to the state postulate, we need three variables to define the state and size of the system. Why pick these three particular properties? To understand this, consider the continuity constraints on an isolated system. Due to mass and energy conservation, the values of n and u can never change. Also, to preserve energy, while not passing any heat or work, the total volume must also never change. In the language of statistical mechanics, we summarize the situation by saying that n, v, and u are invariants of an isolated system. The significance of an invariant property is that we do not need to evaluate it statistically, because no matter what configurations the system adopts due to molecular fluctuations, an invariant property remains constant. With n, v, and u fixed, quantities such as kinetic and potential energy, momentum transfer rates at surfaces, and so forth, will fluctuate with time. Thus, for these quantities to be meaningful as state properties, we need to calculate the statistical average. For example, in our examination of a 2D Lennard-Jones fluid, we calculated the time average translational kinetic energy by numerically integrating the kinetic energy over a particular time interval, t1 to t2, and then dividing by the length of this interval, t2 minus t1. For short averaging times, the value of this average depends strongly on the choice of time interval. However, as t2 minus t1 gets longer, this time average value converges on a stable value. This convergence occurs when t2 minus t1 is long enough for the system to have visited a representative sampling of molecular arrangements. For a real molecular system, how long does t2 minus t1 have to be for the average to be meaningful? For gases and liquids, it might only require a few picoseconds. However, for very complex systems with both frequent and infrequent events, it can be much longer. A classic example is protein folding. Although the motion of solvent molecules in individual atoms within a solution with protein dissolved in it are fast, the coordinated motion required for the protein molecule to change its tertiary structure, i.e. its state of folding, might be milliseconds or even longer. This disparity of timescales between short-time and long-time events adds yet another hurdle to accurately modeling macroscopic behavior based on the time average motion of individual molecules. However, intuitively, we might expect that for any system of molecules, there is an element of randomness to its time evolution. Indeed, a fundamental postulate of statistical mechanics based on this idea of randomness is the Ergodic Hypothesis. The Ergodic Hypothesis states that due to random fluctuations, the molecular configurations acquired by a system of constant n, v, and u over a finite time period are statistically representative of all possible configurations, sharing these same values of n, v, and u. If this hypothesis is correct, we should be able to work backwards. Specifically, if we can evaluate the statistical probability of any given system configuration, we should be able to calculate statistical averages without knowing the detailed time evolution of the system. What do I mean by the term configuration? Thinking classically, a configuration of the system is any distinct set of positions and momenta of the individual atoms and molecules. For example, shown here are three distinct configurations of the 2D Lennard-Jones fluid at a particular value of n, v, and u, obtained by pausing the simulation and examining the positions and velocities of the individual molecules. If any of these positions and velocities are different by some prescribed tolerance from the values at another time, it constitutes a distinct configuration. Note that the term configuration is quite different from the term state, which refers to the macroscopic variables describing the system as a whole, in this case n, v, and u, which are shared among all possible configurations. Configurations are also sometimes called microstates. The micro in this case is not a reference to physical size. It reflects the idea that any given thermodynamic state is comprised of many, many possible individual configurations. How many different possible configurations are there? As you can imagine, for any macroscopically sized group of molecules, it's going to be a very, very, very big number. We'll get back to exactly how big this number is for molecular systems, but for the moment, let's assume it's a finite number and give it the symbol omega, defined formally as the number of unique system configurations sharing the same value of n, v, and u. This quantity has many names in the literature. In statistical mechanics, it's often called the microcanonical partition function, but that's quite a mouthful. I personally prefer the term multiplicity, a mathematical term that highlights its meaning as the total number of unique configurations acquired by a permutable system. To better understand how the ergodic hypothesis benefits us, consider taking a time average of some property f of the system over a hypothetical time interval, t2 minus t1, that approaches infinity. In principle, the system will eventually visit and revisit every possible system configuration sharing the same values of n, v, and u an infinite number of times. This being the case, suppose that during this infinite meander through time, we record the total cumulative time, tj, the system spends in each uniquely identifiable configuration, j, where j is an index spanning 1 to omega. We could then calculate the normalized probability of finding the system in that particular configuration as tj divided by t2 minus t1. By normalized, I mean that the individual probabilities sum to 1, as ensured by the fact that the cumulative time spent in each configuration must sum to the total time period, t2 minus t1. Now consider what happens to our time average as t2 minus t1 approaches infinity. By definition, integration is really just a sum over infinitesimally small time steps. During each of these steps, the system will be in one of its many possible configurations j with property fj. Since the sum does not depend on the order of summation, we can collect together all subintervals of the integral that share the same configuration j. During these subintervals, the value of f is fixed at value fj. Thus, the integral can be re-expressed as a sum of fj times tj. This sum, in turn, can be re-expressed as a sum over fj times the normalized probability of finding the system in configuration j. In other words, the time average of a fluctuating quantity over an infinite time period is equivalent to a time-independent weighted average over all possible system configurations. This latter type of weighted average over configurations rather than time is called an ensemble average, where the word ensemble refers to the ensemble of possible system configurations, the total number of which, in this case, is the multiplicity. Workers often distinguish this type of average from a time average by using angled rather than straight brackets. For a molecular system of macroscopic size, i.e. 10 to the 23rd molecules, the multiplicity is so large that the time required to visit all possible system configurations is much, much longer than the age of the known universe. This is where the Ergodic hypothesis comes in. We assume, due to randomness and similarity among many of the possible system configurations, that even over a finite time interval, the time average behavior is given by the global ensemble average. This is an incredibly powerful assumption, since we no longer need to worry about the detailed time trajectory of the system. Instead, our attention shifts toward understanding how system properties depend on the system configuration and the relative probability of different configurations. To that end, a second key postulate of statistical mechanics is that systems of molecules are microscopically reversible. Microscopic reversibility simply means that energy-conserving collisions among molecules cannot be biased in one direction. For example, shown here is a video of two Lennard-Jones molecules colliding and interacting over a brief period of time. In the video on the left, after some time elapses, I press the reverse button, which inverts the velocities of the two molecules, sending them back along their previous path. In the right video, I simply reverse the direction of the movie, playing the previous forward motion backward. Can you tell the difference? It's impossible to tell because of the time inversion symmetry of Newton's laws of motion. A consequence of this reversibility is that there's no way for a system governed by such collisions to evolve from one configuration to another in a particular direction. A full justification of microscopic reversibility in molecular systems is beyond the scope of this discussion. However, it's rooted in quantum mechanics and the inherent symmetry of all molecular-level energy exchange events. A common misconception in thermodynamics is to confuse microscopic reversibility of individual molecular interactions with macroscopic reversibility of groups of molecules. For example, adding a few more molecules to the previous simulation, we can set up a billiard game and see what happens when we crash a molecule into its friends. After a short time period, I reverse the direction of the molecules and compare to the previous collision being played backward. Even though the motion of the molecule seems random after the collision, we see there's actually some hidden order in the classical motion, and this refocuses the energy in a seemingly unnatural way, at least for short time periods. However, what happens if we wait a lot longer before reversing the direction of the molecules? Even with 64-bit accuracy of the simulation, tiny errors accumulate in the calculated trajectories, and this slowly erodes this hidden order. Finally, after a few minutes, we reverse the direction of the molecules and see what happens. As you can see, any memory of the collisions is no longer retained by the system. You might be thinking that the laws of classical physics are not limited by the accuracy of a calculation, so in the real world the molecules would retain their hidden order. However, as I showed you in a previous episode, molecules are not classical, they're quantum mechanical. The Heisenberg uncertainty principle places orders of magnitude greater uncertainty on the positions of the molecules than the simulation does. We can see this by taking a look at the wave packet simulation I showed you last time. This time, however, let's take it off the GIF loop and let it run a bit longer. You can see that after a few traverses of the box, quantum coherence is completely lost, corresponding to complete loss of any knowledge of where the particle actually is. So the idea of a hidden order among molecules is really illusory. a feature of classical physics that does not translate to real molecules, which have an inherent quantum mechanical tendency to randomize. An interesting illustration of the impact of microscopic reversibility is Maxwell's demon, a thought experiment developed by the Scottish physicist James Clerk Maxwell. In this thought experiment, an isolated system of molecules is separated into two compartments by a rigid wall. The wall has a single door of molecular dimensions, staffed by a small demonic creature. If a molecule approaches the door from below, the demon opens the door and lets the molecule through to the upper chamber. However, if any molecules approach from above, the demon closes the door, preventing its exit from the upper chamber. Due to random motion over time, the molecules eventually all collect in the upper chamber. This process, as described, violates microscopic reversibility, since the interactions of each molecule with the demon is not time reversible. So according to the laws of physics, it can't happen. As an example, shown here is a modified version of our Lennard-Jones model, which includes a wall with a small trap door. This door is constructed of molecules connected by stiff bonds to a wall of stationary molecules, shown in gray. The molecules are arranged such that any free molecules of sufficient velocity approaching from below can push their way through the door without very much stretching of the bonds. However, due to the geometry, any molecules approaching from above must stretch the bonds much further to get through. Does this actually work? Shown here is what the system looks like immediately after starting the simulation and several actual hours later. As you can see, no systematic concentration of the molecules in the upper chamber has occurred, even after millions of total collisions. Examining the trajectory of the individual molecules reveals why. At any finite temperature, the molecules comprising the door come to thermal equilibrium with the gas molecules, so are bouncing around just as violently. These motions, just like the free motion of the gas molecules, are subject to the same rules of time reversibility of Newton's laws. So it's not possible to tell if the simulation is running backwards or forwards. This also means it's impossible for the door or any other door constructed of thermally equilibrated molecules to do what Maxwell's demon is supposed to do. A further consequence of microscopic reversibility for ergodic systems is something called the equal probability postulate. Quoting David Chandler once again, the equal probability postulate states that for an isolated system of fixed n, v, and u, all system configurations, i.e. microstates, are equally probable. The justification for this postulate is non-trivial, but can be proven by examining what happens to a system subject to energy-conserving and microscopically reversible molecular interactions. Restated mathematically, this statement implies that for a system of constant n, v, and u, the normalized probability of any given configuration J is given simply by the reciprocal of the multiplicity. This further implies that the ensemble average for any property of an isolated system is given simply by a sum of Fj over all configurations, divided by the total number of configurations. Let's take a moment to think about what that really means. Here are three configurations we looked at earlier for a system of 576 molecules in a box of volume 1024, with total internal energy minus 830. Here is yet a fourth molecular configuration, D, with the same values of N, V, and U, with all the molecules nicely aligned in rows, with zero velocity and zero kinetic energy. What are the chances of that ever happening spontaneously? Yet according to the equal probability postulate, configuration D is equally likely as configurations A, B, or C. What? When most people are presented with this suggestion, they have to fight their intuition, which usually is screaming at them that A, B, and C are way more likely to happen. The mental illusion at work here comes back to the boy in the cartoon. We don't see the configuration of his messy room as unique because of our association of neatness with uniqueness and disorder with likelihood. But as I said earlier, neatness or messiness is just a value judgment. It does not make a given configuration more or less unique. In the case here, configurations A, B, and C each involve a specific unique set of positions and velocities of the molecules, so they are just as infinitely unlikely as configuration D. In fact, any particular configuration we can think of is impossibly unlikely, since the multiplicity is so overwhelmingly large. So why is our intuition so strong that configurations A, B, and C are more likely? One thing you might notice is that A, B, and C all look rather similar qualitatively and have similar kinetic energy, spanning a narrow range from about 270 to 290. To explore this a bit further, here is the same system after reaching equilibrium. Just watching this for a minute or so, we can see the system evolves from one configuration to another, to another, to another, each of which is equally unique and unlikely. Yet most of them look rather similar and have a similar instantaneous kinetic energy of about 280. This implies there's an overwhelmingly large total number of configurations similar to A, B, and C, while there is only one configuration D. The consequence of this is that the ensemble average of the kinetic energy will be weighted toward the properties of configurations similar to A, B, and C. In other words, it's not the likelihood of any one configuration that matters. It's the sheer number of configurations sharing similar properties. If this were a course on statistical mechanics, we would, at this point, delve more deeply into the subject of predicting properties based on ensemble averages. We don't really have time to develop that here, so we'll have to leave the subject for another course. However, a chief takeaway message is that the probability of any given configuration is reciprocally related to the multiplicity, omega. This suggests that multiplicity itself is an important state property that determines the direction of spontaneous processes. To see this, imagine an isolated system of an insulated box containing an ideal gas. The gas, which occupies volume V0, is confined to the lower half of the box by a membrane. We now rupture the membrane. What will happen? Intuitively, you expect the gas to expand to fill the entire space, 2V0, while the number of gas molecules N and total energy U remain the same. Why does the gas spread out like this? To understand this, consider the case of a single molecule in the lower half of the box before rupturing the membrane. How many different configurations can this one molecule acquire? It's going to be a really big number, but will it be an infinite number? Those of you studying the particle in a box problem in quantum chemistry already know the answer to this question. For a given energy, there is actually only a limited set of degenerate states due to quantization of the translational degrees of freedom. So yes, at ordinary temperatures it will be large, but a finite number. Let's call this number omega 0. Now we rupture the membrane. What happens to the multiplicity? Speaking classically, since the kinetic energy is the same, and thus the velocity remains the same, the only difference is the available space. This implies the number of possible configurations will double, since the molecule has twice as many places to be. This also agrees with quantum mechanics, which predicts the number of degenerate states will, on average, double when we double the size of the box along one of its axes. Okay, so now consider two molecules. Assuming the molecules are non-interacting, for each possible configuration of the first molecule, there will be omega 0 available configurations for the second molecule. Thus, the total number of configurations will be omega 0 squared. Following our previous logic, doubling the volume doubles the number of configurations for each molecule, resulting in a total multiplicity of 2 omega squared, which is 4 times greater than the multiplicity before doubling the volume. Adding another molecule, we get a multiplicity 8 times greater than when we double the volume, and so on. Thus, for n molecules, the multiplicity of the system grows by a factor of 2 to the n upon rupturing the membrane. So what if n equals Avogadro's number, 6.02 times 10 to the 23rd molecules? In this case, the multiplicity grows by a factor of 2 to the power 6 times 10 to the power 23rd, which after logarithmic conversion is about 10 to the 2 times 10 to the 23rd power. Note that this is not 10 to the 23rd, which is itself a big number. This is 10 to the 10 to the 23rd. In other words, a 1 followed by 10 to the 23rd zeros. That is an unfathomably large number. Meanwhile, the original ensemble of omega to the n configurations of the original system are not gone. They remain a subset of the new, much larger ensemble of configurations. However, the probability of the system being found in one of these original configurations is 1 over 2 to the n. This is a very small number. In fact, it is so small that the age of the universe is orders of magnitude too short for it to ever happen. In other words, anytime we release a constraint on a large group of molecules, they have an overwhelming and irreversible tendency to adopt new configurations not previously available. This basic principle is codified in something called the second law of thermodynamics, which states that the multiplicity of an isolated system can never spontaneously decrease. It can only increase. If this doesn't sound quite right, perhaps it's because you've heard multiplicity described slightly differently. If we take the logarithm of the multiplicity and multiply by a constant, we get another state property called the entropy. If you're surprised at this point to hear that, then I've successfully lured you into my mental trap, intended to challenge any preconceptions you may have about what entropy really is. According to this definition, entropy is not a measure of disorder at all. It's actually much simpler than that. It's the log of the number of configurations. And that's really all there is to it. This incredibly simple but powerful definition of entropy is enshrined on the grave of the person who realized all this, Ludwig Boltzmann, for whom Boltzmann's constant Kb is named. In principle, the choice of constant relating multiplicity to entropy is arbitrary. It could be 1, for example. However, as we'll see later, the choice of this constant as Boltzmann's constant makes life easier when using a previously established temperature scale, in this case Kelvin. This leads to a slightly revised, perhaps more familiar statement of the second law, which is really equivalent, which is that the entropy of an isolated system can never spontaneously decrease. It can only increase. Based on Boltzmann's definition, you might wonder why it's necessary to define entropy at all. The multiplicity itself is a perfectly legitimate thermodynamic state property that contains the same information as the entropy. Is this just a historical quirk? Although workers did conceive of entropy prior to this definition, that's probably not the main reason we use it today. The main issue is that multiplicity itself is an extremely awkward thermodynamic property to use. One problem is that, as we've seen, multiplicity is an unfathomably large number, which can change by many orders of magnitude upon tiny changes in conditions. The second problem is that multiplicity is neither intensive nor extensive, and thus does not conform to our usual rules for the behavior of state properties upon changing the size of the system. To understand the latter point, consider what happens when we combine, not mix, just combine, two separate systems A and B with identical intensive properties, molar volume V and internal energy U, but different total numbers of molecules, Na and Nb. Since the intensive state of the systems are the same, then according to the state postulate, all other intensive properties are identical. Thus, if multiplicity were intensive, the multiplicity of system A, system B, and the combined system would all be the same. In contrast, if multiplicity were extensive, the multiplicity of the combined system would be the sum of the multiplicities of the two systems. However, probabilities are multiplicative, not additive. To see this, consider for a moment all the possible configurations that the combined system could acquire. Since the two systems are unmixed, then for each specific configuration of system A, there will be omega B possible configurations of system B, and vice versa. Thus, the total number of possible configurations in the combined system is omega A times omega B. This is neither intensive nor extensive. But what if we take the logarithm of the multiplicity? When we do this, we see that the log of omega obeys the combining rules for an extensive property. Thus, if we define entropy as a constant times the log of the multiplicity, it's extensive. Meanwhile, we can also define a molar or mass-specific entropy by dividing extensive entropy by the number of moles or mass. Since the two systems here are intensively identical, their molar entropies are the same, as is the molar entropy of the combined system. Given this definition of entropy as the log of the multiplicity, how do we reconceptualize what's happening in our cartoon? Drawing a direct analogy to the MD simulations we looked at earlier, what we're looking at in this drawing is not really a state of the boy's room at all. It's a configuration of his room. This particular configuration is merely one of many possible configurations making up the state of his room. This state includes both neat and disorderly configurations. If he's anything like my own son, if we left him for a few hours and came back, we'd find the room in a completely different configuration, perhaps a bit messier, perhaps a bit neater if he decided to clean it up a bit. This does not mean entropy of his room is going up and down. Entropy as a state property encompasses all these configurations, not just one of them. Based on these considerations, a better colloquial description of entropy is probably freedom to occupy different configurations. In this cartoon analogy, low entropy is a room with all the toys locked in the closet, limiting the ways they can be rearranged. High entropy is a room with a boy and an unlocked closet, which can have many possible configurations. What makes it high entropy is the unlocked closet and the boy, not the mess. Thus the boy's excuse, "I blame entropy," is actually a fairly accurate statement of the second law. There are many more messy ways the toys can be arranged than neat ones, so in the absence of any constraints on object placement, the room is going to be on average predictably messy. But this is a consequence of entropy, not the definition of it.